Hello, everyone. My name is Jeff Rutherford. I'm a PhD student at Stanford University working in the Brant Lab, and I'm presenting from my hometown of Edmonton, Alberta. I wish I could be presenting under better circumstances and to all of you in person, but here we go. So I will be, let me just share my screen. I'll be presenting on a paper I've been working on for the last 2 years or so of my PhD with a number of excellent co-authors who I should also acknowledge. The title of the study is Closing the Gap, Explaining Persistent Underestimation of US Oil and Natural Gas Production Methane Inventories. Our motivation in this session is all the same. We are concerned about methane as it relates to climate change. Atmospheric methane concentrations are rising, and this is a concern based upon the high global warming potential of methane relative to CO2. Contributions of methane into the atmosphere are from both anthropogenic and natural sources. And according to the US EPA's greenhouse gas inventory, 28% of these total methane emissions are attributable to the fossil fuel supply chain from unintentional leaks and intentional events. Now, we say 28%, but recent evidence suggests that this contribution could be much higher. Now, how do people measure or estimate contributions of methane emissions from various sources? There are a number of different techniques which can be classified according to scale in both space and time. At the broadest scale, we have top-down estimates, which rely upon satellite data, measurements from planes or atmospheric measurement towers. One example is the recent Zhang et al. Study of the Permian Basin. At the more granular scale, you have bottom-up estimates, which can be further classified as site level or component level. Site level includes measurements from downwind samples in trucks or drones. An example is the synthesis study by Alvarez in the journal Science. Component level measurements, on the other hand, rely upon handheld devices, such as high flow samplers. These are at the most granular level, where measurements are taken directly at the component. Now, the EPA greenhouse gas inventory relies heavily upon component level measurements because it allows for a very granular breakdown of emissions at the equipment level. Now, because it's the national inventory, it's used by the government and policymakers in developing methane mitigation policy. Therefore, it is very important that the EPA greenhouse gas inventory is accurate. Unfortunately, a common trend in the recent methane literature has been the persistent underestimation of the EPA's greenhouse gas inventory relative to other top-down and facility-level estimates. For example, in the recently mentioned Alvarez et al. 2018 site-level synthesis study, they find a difference in their site-level national estimate of the greenhouse gas inventory of 60%. I should also mention that this is commonly referred to as the top-down, bottom-up gap. Now, further analysis by Omar et al. Using similar techniques to the Alvarez study, or site-level techniques, they found the largest discrepancy in the production segment. Looking directly at the production segment, they find their site-level estimate of national US emissions within the production segment to be twice that of the greenhouse gas inventory. So based upon this brief review of the literature, there are still open questions. Why exactly does this top-down, bottom-up gap exist? So this is the question that we aim to answer with this study. We specifically focus on the production segment because this is where we find the largest gap to exist. So we can break down our study into 3 separate parts. First, we develop an alternative inventory approach and construct a bottom-up methane emissions estimation tool. Second, using our tool, we estimate US fossil fuel production segment methane emissions and compare this with the site-level estimates from Alvarez and O'Mara, and also with the greenhouse gas inventory. Finally, we do a deep dive on the greenhouse gas inventory emissions factors and aim to reconstruct these emissions factors, comparing our detailed analysis of these emissions factors with emissions factors from our own bottom-up tool. So before I go into the results, I'll explain briefly how these bottom-up tools work. So these bottom-up tools essentially consist of two successive extrapolations, where at each step, emissions factors, or emissions per unit device, are multiplied by activity factors, or counts of devices. The first extrapolation is from the component level to the equipment level. The second extrapolation is from the equipment level to the basin or national level. So in the first step, which is shown in this first panel, we start with our database of component level measurements. And this database is represented by the figure, which is log on the x-axis, probability distribution of emissions per unit component. So with this database, we iteratively resample measurements and we successively resample according to activity factors or counts of devices. Summing across components, we develop equipment level emissions factor distributions, which are represented by the probability distributions broken down by oil field equipment and gas field equipment. Similarly to before, in order to extrapolate to the next level or nationally, we iteratively resample these distributions according to counts of wells and counts of other well pad equipment such as separators, dehydrators, etc. In this way, summing across all equipment, we can arrive at probability distributions of nation scale emissions. So now I'll show you guys some results. So first we perform a model validation and compare our total emissions with two site level studies, Alvarez et al. And O'Mara et al. Again, these are similar site level studies with similar approaches, but one, the Alvarez study gives us total emissions and the O'Mara et al. Study gives us probability distributions. So first, looking at the panel on the left, we have the total 2015 production segment methane emissions. Our study, which is the bar on the far left, matches within uncertainty with the estimate by the Alvarez et al. Study. Further, both of our estimates are approximately twice that of the estimate in the greenhouse gas inventory. So the panels on the right give us probability distributions of site level methane emissions. On the top is a cumulative distribution, and on the bottom is a probability distribution. Both of these, we find similar agreement. In particular, we find agreement near the tail, because on the right-hand side of these plots, we have the high consequence or high emissions, but low probability events, which are often referred to as super emitters. And this is a common reason why people say this top-down, bottom-up gap exists. What we find is using our new method, we're able to find agreement and replicate this super emitter behavior. So now that we've validated our approach, let's dig into some more details. Based on the bottom-up approach of our analysis, we're able to distinguish sources of emissions at a granular level, much like the greenhouse gas inventory. Specifically, we can investigate sources of differences with the greenhouse gas inventory. So here we've broken down emissions by emissions class, including equipment leaks, pneumatic controllers, tank emissions, completions and workovers, liquids and loadings, and compressor slip. Emissions from our study are shown in red. Emissions from the greenhouse gas inventory are shown in green. we find the largest discrepancy exists with equipment leaks on the far left and tanks in the middle. Specifically, we find a 1.4 teragram difference for equipment leaks and a 2.1 teragram difference for tank venting and leaking events. So what I'd like to do now for the final area of this presentation is to investigate these areas and try to better understand the fundamental reason for these discrepancies. So we'll start with equipment leaks, and because of the time restrictions of this presentation, I won't have time to look specifically at tanks here, but feel free to ask me questions later. So in order to better understand these discrepancies, we need to dig into the underlying data of the greenhouse gas inventory. Specifically, the GHGI sources the greenhouse gas reporting program for tank flashing and venting emissions. And for equipment leaks, they source a study conducted in the mid-1990s by the Gas Research Institute. So like I said, we'll be focusing on equipment leaks, so I'll talk briefly about this mid-1990s data set that they source. So I'll emphasize here that sourcing this data was not an easy task. There are a number of complicating factors. First of all, the GHGI separates emissions factors for natural gas systems and petroleum systems. For natural gas systems, equipment level emissions factors are sourced from this 1996 Gas Research Institute study, which itself was not a primary data collection effort. Rather, it itself draws its data from two studies also published in the early 1990s, one by Star Environmental and another by the American Petroleum Institute. Much of this underlying data is difficult to obtain. Adam and I needed to order these data sets from API, and these paper reports needed to be purchased, scanned, digitized, and then checked for accuracy. A very time-consuming task. So we produced decomposition plots like this for various pieces of equipment. And I should also mention that this GRI report separates natural gas emissions factors on the basis of region. So here we show Western gas systems, and we decompose the emissions factors for gas wellheads. So the equipment level emissions factor is shown on the right, and then it's decomposed into its constituent parts, namely component level emissions factors on the far left, fraction of components leaking in the middle, and then activity factors or number of components per equipment in the third panel. In the interest of time, I won't review every element of the decomposition, but I'll focus on the component level emissions factors or emissions per component in the far left panel. So what we find, as you can see for connectors, valves, and open-ended lines, the range of emissions factors for our study are shown in black bars. The EPA mean is shown in red, with the mean value black square. So as you can see, there's nearly an order of magnitude difference between mean component level emissions factors for our study and that of the Gas Research Institute report. And we find that this could be explained by one of three reasons. Either the EPA data is outdated and unrepresentative of today's conditions. Two, could be drawn from a biased sample due to the volunteer selection bias. Or three, does not adequately capture super emitters in the quantified data. So to conclude our study, we've developed a bottom-up approach validated within uncertainty by previous site-level estimates of US production segment CH4 emissions. We found our estimate is nearly 2 times that of the GHGI, much like the previously site-level studies by Alvarez and O'Mara. This bias is largely driven by differences in equipment leaks and tank venting. These inventories need to be improved based upon their importance for methane mitigation policy. Our results suggest that emissions factors could be improved using the approach described here. And then pointing to the differences with tank emissions. Non-compliant tank vents and tank equipment malfunction are a significant source of emissions that should be studied more. Finally, we should regularly validate equipment level emissions factors with randomly sampled site level emissions estimates. So feel free to ask me questions. I believe there'll be some sort of chat function through the MIT Applied Energy Conference website. Thank you very much for watching.